Alright, so this is our third video for AP Chem for Chapter 1, and so we're going to focus on Section 1.6. And so we're going to go into significant figures and uncertainty of measurements, which again should be a review for you from Honors Chem. So, accuracy refers to how close an individual measurement agrees with the correct value. Precision, on the other hand, is how close multiple measurements are to each other. So precision, we are trying to get the same answer over and over again. For accuracy, we're trying to get the right answer. So in other words, obviously we want to be accurate and precise. We want to get the right answer over and over again. However, if we get the wrong answer over and over again, but at least they're close to each other, usually that's easy for us to figure out what's going on. The problem is, of course, that they're just all over the place. That's the hardest way to have to fix a situation, is if they're just kind of all over the place. But really in science, we want both accuracy and precision. So, significant figures. Remember, this is just a review, so I'm going to go super fast. All digits 1 through 9 are significant. Front zeros, or zeros to the left of the significant figures, are not significant. Middle zeros, are zeros in between the significant figures, are significant. And back zeros, or zeros to the right of the significant figures, are significant if you can see the decimal point. It doesn't matter if you know where it is. You have to be able to actually physically see it in the number. And then numbers that are counted and conversion factors contain an infinite number of significant figures. So 12 pencils, that has an infinite number because you would just count that. Or saying 1 kilometer equals 1,000 meters. That has an infinite number of significant figures. So let's go ahead and jump into some. So it says, how many significant figures are in each of the following numbers? Assume that each number is a measured quantity. So see here they didn't give us any units, so we would have no idea if it was something you would count or not. But they said assume that each one is a measured quantity. Okay, well we know that the 4 and the 3 are because they're not zeros, and these zeros are middle zeros. So for this one, all 4 of them would be significant. For part B, whenever you have something in scientific notation, you don't count the 10 or the power as a significant figure. You're only going to look at the front or the coefficient of the number. So we know that 6, 2, and 3 are, because of course they're not zeros. And then this 0 is now a middle zero. So this would also have 4 significant figures. For part C, it says 5,000. So we know the 5 is. So these are what I call back zeros. Zeros to the right of the significant figure. I can't see the decimal point. Even though I know it's right here, they didn't put the decimal point. So these 3 zeros would not be significant. Which is weird because if it was written like this, with the decimal point, then those zeros would be significant. Okay, and I know that's tricky, it's weird, but that's how it is. So, hopefully, this is coming back to you. Okay, it's been a while since we talked about significant figures. So remember, anytime you want to pause and try any of these on your own, that's a great idea. So it says an object is determined to have a mass of 0.01080 grams. How many significant figures are there in this measurement? Okay, well we know the 1 and the 8 are significant. These are front zeros. Front zeros are before the significant figures. Okay, so front, middle, and back zeros have nothing to do with where the decimal point is. They are based on where the significant figures are. So these front zeros, the 0.0, are not significant. They are just placeholders. This middle zero is significant. This back zero is only significant if I can see the decimal point. Well, I see the decimal point right there, so it is significant. So if you look, 1, 2, 3, 4, so our answer would be C for that one. Okay, so really it's just all about the zeros, of course. Like, is it significant or not if it's a 0? So let's move on to practice exercise 2. It says how many significant figures are in each of the following measurements? Well, the first one should be super easy. There's no zeros. So all 4 of them are significant. For part B, again, I told you, when it has the power, like the exponent for scientific notation, don't move the decimal. Don't try to underline the 10 or the 4. Okay, we disregard this part completely. So 2 and 3 are both significant. And then for part C, we know 1, 3, and 4 are. These are front zeros. A lot of you want to underline the first two, or the second two zeros, because you think they're considered back zeros because they're after the decimal. Remember, back zeros are after the significant figures. These are all before the significant figures. So all three of these are front zeros. Front zeros are never significant. They are placeholders. All right, so you should have gotten 4, 2, and 3. So hopefully you got those right. All right, so picking significant figures, hopefully, is very easy for you, but it's the calculations that make them a little trickier. Go ahead and flip my page so I'll be ready for all this math we're about to do. So, when you add and subtract numbers, your answer must have the same amount of decimal places as the measurement with the least amount of decimal places. So remember, when we add and subtract, we're counting decimal places. For multiplying and dividing, your answer must have the same amount of significant figures as the measurement with the least amount of significant figures. So when we multiply and divide, we're counting significant figures. So, nothing we can do but jump on in. So it says the width, length, and height of a small box are 15.5, 27.3, and 5.4 centimeters respectively. Calculate the volume of the box using the correct number of significant figures in your answer. Okay, so I know volume is length times width times height. So I just plug in. So my length is 15.5. Oh, sorry, my length is technically 27.3. I mean, I know it doesn't matter what order, but let me follow the question. The width is 15.5, and the height is 5.4. Okay, and I left out the units on here just because I'm trying to make you look at the numbers only, but we do need to make sure to know they're all 3 centimeters. So once we multiply those, I got 2,285.01, and then what's our unit? Well, centimeters times centimeters times centimeters is centimeters cubed. So remember, y'all, when we're rounding, I'm not teaching you new rounding rules that you learned in math. I'm teaching you where to round. Okay, yes, 5 and up still rounds up. Less than 5 still stays the same or rounds down, however your teacher taught it to you. But what I'm showing you is how do you know where to round? Like, do I want to round right here? Do I want a whole number? Do I need to round up here? That's what I'm showing you. Okay, so we're multiplying, so we're counting significant figures. So 1, 5, and 5 are all significant, so this one has 3. 2, 7, and 3 are all significant, so this one has 3. 5 and 4 are significant, so this one has 2. So remember, our answer needs to have the lowest amount. So that means my answer can only have 2 significant figures. Right now, it has 1, 2, 3, 4, 5, 6. So I need to cut some off. So you just start at the front of the number. So is 2 significant? Yes. Is 2 significant? Yes. That means I need to stop and round there. The problem is a bunch of y'all will then round that to 23. Well, that doesn't make any sense. You can't say, oh, it's 2,285.01. That's about 23. It's not about 23. If you have to count off actual places before the decimal, you need to fill in zeros. Okay, so 2,285 is about 2,300 centimeters cubed. Or, if you don't like filling in zeros, you can change it to scientific notation. We can say, okay, well, it's about 2.3 times 10 to the 123 centimeters cubed. You can do either. Both of these numbers have 2 significant figures, so both of them are acceptable. All right, so again, hopefully this is a review. It's bringing things back that were already in your mind. Okay, so like I said, you can do either one. All right, so let's see what happened with Ellen. Ellen recently purchased a new hybrid car and wants to check her gas mileage. At an odometer setting of 651.1 miles, she fills the tank. At 1,314.4 miles, she requires 16.1 gallons to refill the tank. Assuming that the tank is filled to the same level both times, how is the gas mileage best expressed? Sorry, I guess we're doing this again. All right, so the first thing I need to do is figure out how many miles she traveled, because we have an ending amount and a starting amount. So I'm going to start by subtracting. So So I'm going to do my 1,314.4 miles minus my 651.1 mile. So once I do that, I get 663.3 miles. All right, so I've subtracted, so I need to stop and assess my significant figures. Well, when you subtract, you count decimal places. This number has 1 decimal place. This number has 1. That means I want 1 decimal place in my answer. Well, if you look, I got 1 decimal place in my answer. I don't need to round this number at all. I can leave it just like it is. All right, so then it's asking, what is her gas mileage? Okay, well, gas mileage is usually expressed in miles per gallon. Okay, well, I got my miles, I got my gallons. So per means divide. So I take my miles, 663.3 miles, and divide it by my 16.1 gallons. The other way you could have known is if you didn't realize, look at the units over here. They're all miles per gallon. All right, so once I divide, I end up getting 41.19875,776 miles per gallon. Hopefully we can tell by my answer choices that we do need to round this. Okay, so see, now we're dividing. When you divide, you count significant figures. The good thing is it's super easy because there's no zeros. So 6, 6, 3, and 3 are all significant. So this number has 4. 1, 6, and 1 are all significant. So this number has 3. Remember, I want the lowest amount in my answer. So I want 3 in my answer. So I start at the front. 4 is significant. 1 is significant. 1 is significant. That's 3 significant figures. So I want to cut off right here. So the 9 will round the 1 up, so I get 41.2 miles per gallon. And so then I look over here, well, that would be answer choice C. And that's all you have to do. Okay, so if you have a multi-step problem, you just need to assess your significant figures in between each step. And so again, make sure you're pausing these and trying some of these on your own. Okay, it doesn't help if you just watch me do them all. You already watched me teach this in class in honors. So it takes 10.5 seconds for a sprinter to run 100 meters. Calculate her average speed in meters per second and express the result with the correct number of significant figures. Okay, well, I need meters per second. Well, they gave me meters, so I'm going to put that on top. Per second, 10.5 seconds. All right, so I'm going to divide. When I divide, I get a super long number. 9.523809524. My unit is meters per second, of course. So I'm dividing. So I'm counting significant figures. So we know the 1 is significant. These are all back zeros. They're after the significant figure. I can see the decimal point, so they are all significant. So this number has 5 significant figures. Here, we know the 1 and the 5 are. Middle zeros are always significant. So this one has 3 significant figures. So remember, our final answer should have the lowest amount. So I want 3 significant figures in my answer. So I start at the front. 9 is significant, 5 is significant, 2 is significant. I'm going to cut off right there. A 3 is not going to round 2 up. So I end up with 9.52 meters per second. Just like that. Okay, so again, hopefully you're getting these right. So now let's go to a little bit trickier ones where we have some more of those multi-step ones. Because a lot of you can do it if it's just one step. It's the multi-step ones that kind of throw you off for a loop. Sometimes you just have trouble figuring out what the steps are too. So, all right. So it says a vessel containing a gas at 25 degrees Celsius is weighed, emptied, and then reweighed as depicted in the figure. So here we have a mass of 837.63 grams. Here we have a mass of 836.25 grams. So this is when it's full. They pull the gas out of it. This is when it's empty. And then it tells me the volume right here. It says calculate the density of the gas. Well, we know density is mass over volume. But the thing is, we just want the mass of the gas. So in here, when they weighed it, they had the gas and the flask that it's in. So what I need to do is I need to take my two values and subtract them first to get my mass. Okay, so, and I know these numbers are probably hard to see up here, but they're on your paper too, which if you're looking at my paper, it's also hard to see. So I'll be writing the numbers over here. So our starting amount is 837.63 grams minus the empty container, which is 836.25 grams. So I'm going to subtract first. So when I subtracted, I got 1.38 grams. So I'm subtracting. So my answer needs to follow decimal places. So this number has 2 decimal places. This number has 2 decimal places. That means my answer should have 2, which it already does. So I don't have to round this number. And see, that's the thing with significant figures. Sometimes you don't need to round. All right, now I need to do density equals mass over volume. Now you may be thinking, whoa, wait a minute, where's volume? It's surprisingly right here. I know it's hard to see. It's 1.05 times 10 to the 3 centimeters cubed. Okay, so I put my mass on top, my 1.38 grams, divided by my 1.05 times 10 to the 3 centimeters cubed. And so then I just divide. So once I divided, I got a super long number, 0.0013142857. And then of course my unit is grams per centimeter cubed. But clearly I'm going to have to round that thing. So we're dividing, so now we're counting significant figures. So the top one's easy. None of them are zeros. All 3 are significant. The bottom number, remember, we don't count the 10 or the power. We know 1 and 5 are, and that 0 is a middle 0. So it's also significant. So that means I have 3 in both of my numbers, so I need 3 in my answer. So this is where you have to be careful. Front zeros are not significant, but you still keep them. Okay, you're just going to see me move past them. So this is not significant, so I move on to the next one. Not significant, still a front 0. Move on to the next one. Not significant, still a front 0. So here's one significant figure, the 1. The 3 is the second one. The 1 is the third one. So I'm going to stop and round there. But notice when I write my answer, I'm still going to keep the insignificant zeros. Just because they're not significant doesn't mean they go away. It just means they're placeholders. So my answer would be 0.00131 grams per centimeter cubed, because of course a 4 is not going to round a 1 up. Or of course you're more than welcome to put it in scientific notation if you prefer. And you could do 1.31 times 10 to the 123 negative 3 grams per centimeter cubed. Either one works. Okay, just make sure you're rounding at the correct location. And just remember, all 3 of these zeros are front zeros. A front 0 is before the significant figures, to the left of the significant figures. All right, so hopefully you are not struggling with these. Again, if you are, it's going to get rough. All right, so again, if you haven't been pausing these to try any of these on your own, please make sure you try some of these. All right, so you are asked to determine the mass of a piece of copper using its reported density of 8.96 grams per milliliter and a 150 milliliter graduated cylinder. First, you add 105 milliliters of water to the graduated cylinder. Then you place the piece of copper in the cylinder and record the volume of 137 milliliters. So see, I can already tell I'm going to need to subtract to get the volume of the copper. What is the mass of the copper? Okay, so we have the density, and we can figure out the volume using these 2 numbers. Okay, so let's do that first. So the copper and the water had a volume of 137 milliliters. Just the water was 105. Decided to write my 0 first, I guess, but I didn't do a good job. All right, so once I subtract, I'm going to get 32 milliliters for the volume of the copper. So I'm subtracting, so I need to count decimal places. So this has no decimal places. This has no decimal places. My answer already has no decimal places, so I don't have to round. Right? We are looking for mass. So density equals mass over volume. If I'm looking for mass, I need to multiply both sides by volume. So mass is volume times density. So then I just plug in. So the volume I just calculated was 32 milliliters. And my density is 8.96 grams per milliliter. Okay, so once I multiply those, I ended up getting 286.72 grams, because of course my milliliters cancel. So now we gotta stop and do significant figures again. Well, this time I'm multiplying, so it's based on significant figures. So 3 and 2 are significant, so that number has 2. 8, 9, and 6 are significant, so that number has 3. So remember, we want the lowest amount, 2. So I start at the front, 2 is significant, 8 is significant, so I'm going to stop there. So remember, y'all, you can't just cut off the 6, you need to change it to a 0. 6 is going to round the 8 up, so you can either put about 290 grams, or like I said, if you prefer scientific notation, you can do 2.9 times 10 to the 2 grams. Either one works. All right. Oh, sorry, and then we got to select our answer here. So let's see, what do they have? Okay, so it'd be this right here, 2.9 times 10 to the 2, which of course is just 290. All right, so hopefully you got that right. Remember, if you haven't been trying them, we got one more. So please try this last one if you haven't been trying the other ones. All right, so if the mass of the container in the sample exercise were measured to 3 decimal places before and after pumping out the gas, could the density of the gas then be reported to 4 significant figures? All right, ooh, I wish I didn't just erase that. All right, so it's saying that if the mass of the container was measured to 3 decimal places before and after pumping out the gas in the sample exercise. Okay, so let me go back one more. So here, if you look, our density, we could go out 3 significant figures for our density right here. Okay, it's saying that if our mass of the container was measured to 3 decimal places. So see, right now it's only been measured to 2. Okay, so here I had 837.63 grams and 836.25 grams. So it's saying if we had gone out 1 extra decimal place, could we have gotten an extra significant figure here? Well, if we had an extra decimal place, that means yes, when we subtract our masses, we would have an extra significant figure for our masses. So once I subtracted to begin with, I got 1.38 grams, and that was 3 significant figures. I would have had a 4th one here. However, remember, then I had to do density equals mass over volume. So I would put my 1.38 grams, but I would have an extra number here, but I would still have to divide by my volume, which is 1.05 times 10 to the 3 centimeters cubed, and my volume still only has 3 significant figures. So since I still only have 3 significant figures here, even if I had 4 up here, I could only have 3 in my answer. So your answer would be no, because volume is still keeping it at 3. All right, so again, hopefully this is all review. You should already know this. That's why I'm not covering any of this in class. If you're struggling at this point, you may need to go see the counselors and look at a schedule change.